this is Professor Chen. Here, I want to give you the second head up of the chapter 2. And today, we're going to briefly introduce Poisson Ratio and the Generalized Hookes Law, and then also preview the stress concentrations. The first one, we talk about Poisson Ratio. What is Poisson Ratio? For any elastic material, you see, if I stretch in the axial longitudinal direction, you can observe the lateral reduction. And so in graphically, we can mention this one. This is the original, for example, model. And that is the dimension here. Say, for example, I call this is delta x in this direction, and the dimension here is delta y. And when this is under loading, for example, the loading applied in the x directions, so this model is going to deform, and then let me overlap the deformed model to the original undeformed and using the pink one. And here I do this schematic drawing. So from here, this one I exaggerate. This is the stretching, and the stretching here. Let me call the delta x. Sorry, excuse me. This one should be Lx, not to use the same symbols. And the lateral reduction here, let me call the delta y. Sorry, here let me change it. This dimension is Ly here. So the Poisson ratio, we using the symbol mu. The mu, by definition, is the lateral strain divided by the axial strain. Axial direction is in which the loading applied. And for this example here, we can put into this is epsilon y divided by epsilon x. And epsilon y, that is a reduction. So implicitly, this is a negative number. So we keep the Poisson ratio positive. So here we artificially add up y minus sign here. So this is the definition of the Poisson ratio. And one more time, the axial direction is in which the loading applied. Lateral direction can be in the direction in the vertical or in out of the board direction here. And the applications of the Poisson ratio can be applied to explain the generalized Hookes law. So we consider, for example, this material, and then say under one direction of the loading and corresponding stress is sigma x. So here we can calculate the deformation or strains for this model in x, y, z directions. For example, the strain in x direction. Now the loading applied in x direction, that is axial loading. So here we have the strain will be equal to stress simply divided by its Young's modulus. And now the strain in y and z directions. Right now, y and z are normal to the loading direction, so they are both lateral directions. So we put into this formula strain equal to the axial strain multiplied Poisson ratio. So axial strain, which is this one, multiplied with Poisson ratio, give a minus. Again, epsilon y equal to Poisson ratio multiplied with the axial strain, put a minus. We simply adopt this form to here. The same thing we put into here. The axial strain equal to this one. Okay, so that is a simple application for this. We consider another example is this. Consider the same material, and right now the loading is not in x. However, that one loading is in y directions, and corresponding stress, let me call sigma y here. So right now, again, y direction is our axial direction. So that is the normal strain equal to the stress divided by Young's modulus simply. And now corresponding to the loading direction, which is y. So x and z right now corresponding is the, we call the lateral directions for this loading case. So again, we adopt this one. The lateral strain equal to the axial strain multiplied Poisson ratio. So here is our axial strain, sigma y. Divided by E, so that is the axial strain, and multiply with Poisson ratio. Okay, the same thing. This is the axial strain, and multiply with Poisson ratio. That gives us the lateral strain. And one more example here, and you could imagine right now I'm going to apply the loading in the z directions. So corresponding the stress, let me call it sigma z. So z direction is our axial direction. So the strain, normal strain would be like this. So now xy corresponding is the lateral strain. So here we quickly write it up like this. Okay, so here if we take the superposition principle, so basically the loading case can be combined. So which means if we take summations, the loading could be like this. This is a general loading case, and for example, this is a sigma loading in the x direction and loading in y direction, and also the loading in z direction. So if we combine the three, basically in concept is we take summations. So here we take the result of the summation together. So here you can see if we take up the summations, epsilon x for this loading case would be the summation of the three terms. Epsilon y for this loading case will be the summation of the three terms. Similarly, epsilon z will be the summation of the three terms for this case. So the summation of the individual terms give us the what we call the generalized Hookes law. And here in these chapters, we will go over a few examples for demonstrating this example here. The final one, we're going to talk about the stress concentrations. And this issue is very empirical, and we're going to learn using a curves, engineering curves, to study this case. And in general, here in this class, we learned going to study two cases. One is this material model is not homogeneous anymore, uniform anymore, but here we have a fillet. And another, the geometry to produce stress concentration is here we have hole. And the stress concentration would happen, let me pick up a cross section here. And then let me show you the stress concentration. So if I pick up that sections and then the free body diagram, let me pick up this one. So along these cross sections, in reality, the distribution of the stress will be like this. So this is a profile here. So here you can see the largest strain. This is a maximum stress here, from here to here. So this is we call the stress concentration. Stress simply concentrate at this point and at this point. And in the similar fashions, if you would pick up the cross sections here and here, then quickly you can identify the concentration. Stress will concentrate at the 2 points. And that is the, we're going to, again, using the engineering curves to calculate what is the maximum stress in such a non-uniform material models. Okay, so that is the head up for the second portion of the chapter 2. Thank you.